My name is Lukas. I'm co-founder and CEO of TACEO, and at TACEO we're working on collaborative SNARKs or coSNARKs. So again, I want to ask you, how many of you have heard about the term coSNARKs or collaborative SNARKs so far? Wow, I expected fewer, but how many know SNARKs? Everybody, I guess, knows SNARKs, and how many know roughly what MPC is? Okay, that's good. So coSNARKs is just a combination technically of MPC and ZK. So everybody's talking about have to combine these privacy-enhancing technologies to make really fully sense, and for use cases, only one most likely won't do the trick. And that's what coSNARKs is trying to do, combining MPC and ZK in a very clever way. And I like to think about why we're needing coSNARKs when we have already SNARKs, and a way like, if you remember as a child, most of you maybe like to play ball, so American football, soccer, whatever. And if you get your first ball that you own it, it's really exciting. You drag it everywhere, you kick it, you throw it, whatever. But the real fun kicks in if you can do this with multiple people, with your friends. So alone it makes sense, and you have use cases. Exactly the type of thing we have with SNARKs. You have, for example, scalability. You have, on the privacy side, you have identity-based schemes, which you can do with ZK only, so with SNARKs only. But once and also one big use case, you can do private transactions. Once you want to move beyond and work with your friends or colleagues or some business partners, you want to have some way to do this in a distributed way without losing the compelling aspects about SNARKs, especially that about privacy. And one way to do is to combine it with MPC and get this coSNARKs out of it. So being more concrete, there are two use cases or two problem spaces that are very interesting where coSNARKs help. So the first one is like very immediate. We have this client-side proving problem, where for some certain applications that are more demanding than maybe just one transaction, client-side proving won't do the trick. You want to outsource your zero knowledge proof generation. And this just holds for the cases where you care about the privacy. I'm not talking today about the case where you only care about scalability, L2 rollups. They don't have the issue with that the witness is somehow non-public information. And in this case, you want to outsource it to a proof market. They are popping up right and left and are really going to reduce the cost of zero knowledge proofs and the latency. But so far they come with the cost that you have to send the witness, and this is the private data in this case, to this proof market. So you expose your whole data to this prover that does the job for you. And second, even if we solve, let's say, client-side proving, we get it efficient enough, every proof can be done client-side, even ZKML, you have this inherent limitation of ZK that you cannot collaborate with more than one party. And this is just a single player issue. So even though we have the ZK-based smart contract networks, you kind of left with a very limited programmability and composability. And what we really want to have is efficient tools for collaborating on private data while also being able to outsource in a secure way. And some words about FAG, because I think it comes up after me. It's like, for the private proof delegation use case, it would be great to use FAG because you get the best trust assumption. Like outsourcing it to an FAG server, it's perfectly. So far, at least, I don't know of any implementation that can do computing a ZK in an FAG program in a manner where client-side proving, outsourcing client-side proving makes sense. And so the real, let's say, unique selling point on collaborative SNARKs is then more on once you want to compute on private shared state. Because once you move about this outsourcing of ZK proofs, you have to have some way to collaborate and then usually use something like MPC. Now I want to walk you through how collaborative SNARKs work and how those different settings, also private proof delegation and private shared state, play out. So this is a slide where the easier or the use case where you just focus on private proof delegation. You have a single user that has some witness that is private and that just needs to outsource the proof generation because the client device isn't powerful enough. Then what the user could do is share it to now not a ZK proof market that we know today, but let's call it for this like MPC-enabled proof market. And this MPC proof market then selects some nodes from a decentralized network that are now going to the actual job of proof generation. And the user client side does the secret sharing of the witness. So basically, the witness is split into 3 parts and randomized so that they can be sent to these 3 different parties. Now, those parties cannot do the traditional SNARKs computation because they only received a secret share and this doesn't give them any clue about the witness. So they have to come do an MPC protocol and do the SNARKs proof generation in the MPC protocol. That sounds quite nice. Usually, everybody agrees that we have to combine technologies, these paths, to make sense. But it's hard today even to make one of them alone efficient. And what's really standing out with SNARKs, collaborative SNARKs, is the performance. So combining MPC with SNARKs doesn't introduce a lot of overhead. And in fact, so we have implemented this. This is the first tooling, general purpose tooling for collaborative SNARKs. It's so far based on Circum, so that's why it's called coCircum. And the coCircum benchmarks you can see, so this is really hard to see here. The blue and the orange one is SNARKGS and the blue one is coCircum. So we are now with the first tooling that just showed feasibility. We match the performance of SNARKGS. Of course, there's something better like Rapid SNARKs that's a bit faster. But we're pretty confident that you can reach this level of Rapid SNARKs also with coCircum once we have done our optimizations. And why is this the case? Why are we confident? Not only because we think, there is so much to optimize and we think we're so good, but there is this fundamental paper from 2022, which is basically the foundation of collaborative SNARKs, where Alex and Dan Bonnet introduced this concept and showed that the takeaway of this paper was whatever you can do with a single prover, you can do in the multi-prover setting without introducing latency to the process, which is quite significant. And mostly is this because 80% of a SNARKs computation is linear stuff, so linear operations. And linear operations do not cost you any communication in MPC, so it's just the same computation, you don't have to communicate. Because the bottleneck in MPC is communication, and communication just occurs when there are non-linear operations. So that's why SNARKs are particularly what we call MPC friendly. So these are operations and computer programs that tend to be very fast in MPC. So before we go on to the private shared state use case, are any questions to this private proof delegation use case?
Is there any initial setup process required? If I compare with ZK SNARK, it requires a trusted setup. For example, it requires KZZ scheme. So that setup is pretty much required trusted parties to come to generate initial variables. So is there any kind of setup required in this coSNARK MPC-based process as well?
So this depends on the underlying proof system. So for example, for Circum, we have implemented as a backend as the proof systems MPC, FIGHT 16 and Blanc. So you inherit these traits that you get from a proof system. If it has a circuit-dependent setup, you also have to do a circuit-dependent setup. If there's none, there's none. So this is, we haven't implemented or designed a new proving system. We did MPC, FIGHT 16 and Blanc so far. And you inherit this from the proving system. So as I said briefly before, this secure proof delegation might only be a band-aid solution if client-side proving gets fast enough. Hopefully, in terms of privacy, you can do for most stuff client-side proving, because it's just, this is the best trust assumption you can get. You won't get better with any other technology. But where ZK really lacks some programmability and composability is when it comes to use cases like marketplaces. So if you have buyers or sellers that want to discover each other and making some transaction, the discovery process, usually if you're starting with a private state, you have to somehow open it to be matched. And how we do it in Web 2 world today is if you have, for example, Tinder or something where there is a matching, you have to share everything with Tinder that they do the matching for you. But if you're in a decentralized setting, who would you send this data to see to make the matches? This would essentially be, again, a centralized operator that can do, that can manipulate this power. And so for the decentralized setting, we really have to do this matchmaking and this the privacy from your peers into the protocol. And that's why technologies like TACEO, FAG, and MPC are needed to enhance the capabilities of ZK and coSNARKs to make this happen. And the same goes for this very typical example where you have poker, on-chain poker, and you have some hidden states about the other persons that you can't share, and you also don't want to share it with an operator. Or in games, often the term fog of war comes up that is usually solved with these technologies. And very abstractly, think just about any function where you have multiple private inputs from different stakeholders. You need some privacy-enhancing technology that goes beyond zero knowledge proofs. So to walk you through one example, we did this demonstration during EthCC, so an end-to-end example, a guessing game where we leveraged the capabilities of coSNARKs. It was a very simple game. So suppose you have 1K, or 1K sits in a smart contract, and user had to guess a number between 1 and 1,000, and whoever gets the highest unique guess wins. And she wins the amount she guessed. So you see, if two people going for 999, they cancel each other out, and the next person wins. So in this case, if you're thinking about a public chain, you can't do this because you're seeing all the history who had guessed which, so which guesses are already there, and you can just, with one guess, eliminate one guess and then go with your guess right at the end and get the prize. With a private chain like Elio just launched mainnet, there's also not the ability to do this on-chain, because then you have sitting all these guesses in these private states, and who should now compare this, who is the winner? You have to do this then again in a centralized spot. So one operator has to open all these private states, and why do we trust this operator? And that's why we need these technologies. And so for the demo, like how this really looks end-to-end is like we had this UI where you could connect your wallet, you entered and submitted a guess, and the guess was then secret shared directly from your phone. And there's then some stuff more going on to make this all really legit, but just to give you the essence, then there were some proofs for the correctness of the commitments, and that the input is between 1 and 1,000 and so on. But the interesting stuff is now to determine the winner. And to determine the winner, you have now these secret shares from, let's say, 1,000 people, and you have to do like a sorting, a deduplicating, just getting the winner out there. And you do this all in coSNARKs. So you're doing an MPC computation, sorting and everything on this on the secret shared data. And in the end, the protocol produces a SNARK. The proof itself looks exactly the same than traditional SNARK. So a coSNARK, a proof that comes out of a coSNARK doesn't look different than a proof of SNARK. So you can just use the verifiers that already exist. For example, in this case, we did go for optimism and just prove it there verified there very easily. The lessons we learned from this were a lot about developer experience, but that the proof generation, as we already expected, is very fast. The really bottleneck is the MPC computation in front before. So this took a while to compute, because also it wasn't optimized in any way. It was really just to showcase the capabilities of coSNARKs. But on another project where we partnered with WorldCoin, we showed what is possible with MPC if you're going like with an applied research and combined engineering, how far you can go with MPC and the computation. So in this case, we MPC-fied the iris uniqueness checks. So once you go to WorldCoin or to these orbs, they scan your eyeball, and then it produces an iris code, which is just a representation of your iris. And this then has to be checked in the database if you're unique, if you're getting a world ID, or if you already have one. And this now is distributed. So with MPC, there is no single operator that controls this database. The database is secret shared. So these are 6 million entries, I guess, for currently, or at least around 6 million. The tricky part is now you have to do an MPC protocol whenever somebody wants to register for WorldCoin. You have to do an MPC protocol and check this whole 6 million database if some of the iris code is close by at one of these 6 million entries. And to give you like how much there's still room for improvement, we started out with the best academic paper, which could like do roughly 1 uniqueness check per day. So this would kind of be very diametral to the growth expectations of the WorldCoin project to just onboard 1 user per day. I think until they hit 1 billion, this would be very, very long. And now we can do 10 uniqueness checks per second, which is kind of the threshold where it makes sense that the system can work. And this was a combination between protocol research, really on the MPC level, combining different MPC schemes in a very efficient way, using the right hardware. But this is roughly 5 orders of magnitude. So there's, compared to ZK, MPC, there's still a lot of room for concrete improvements. So not on the, let's say, asymptotics, but on the concrete numbers that you can improve. And that's usually what users care about. They don't care about if the asymptotic makes sense. If the concrete performance is good enough, that's it. Yeah, just showing where this stands in this WorldCoin tech tree. So this is the whole WorldCoin tech tree, and every time there is a verification, this uniqueness check is now MPC-fied. And this is kind of what the setup looks like in more detail, sharing this iris data with these MPC parties, and if they give you thumbs up, you can get your world ID. So the ultimate vision of the TACEO is to have something like a compute layer security. So you all know this transport layer security, which secures our communication day in, day out now. And we want to see something similar for computation for the internet. I think there's still a long way to go, and this is not a single project effort, but I think the industry is moving in the right direction. And we depart by combining MPC and ZK. So bringing collaborative SNARKs to the developers. And so far we have started with coSNARK, which is on this end, I guess, from developer experience. And then you have something like where you can do this in Rust, which is there. And we want to slowly move to the way that the developer experience gets a lot better, while also improving about performance, because yeah, developers care about, and applications about latency. You cannot introduce a million-fold overhead. There is some threshold where it makes sense, and we have to be under this threshold such that the tech is used. Yeah, and if there's only one takeaway you have from this talk, it's like MPC and ZK together is collaborative SNARKs, and they work pretty well together. You wouldn't, maybe the intuition, at least mine before we read the paper, wasn't that this would work out that good. Thanks.